In the last video, I showed you how to run a multi-scale simulation that looks like this. Now, this was a very simple circuit setup, simulation setup, and so chances are you'll be able to set everything up and the simulation will run correctly. But in a real application, you often have downstream LPN circuits that are very complex. And so often you can set up the whole simulation and it either would not run or would not run properly to give you the correct results. And so in those cases, it's often very helpful to take your multi-scale simulation and test it by only running the 0D part. And so without running any simulation for the 3D part. And in this video, I'm going to show you how to do that. Now, before I tell you how you can do that, let's think about what situation we have if we were to run this multi-scale simulation without the 3D part. So here you've got an outlet that's coupled to an RCR circuit. Now, when you think about the elements that you have here, the first element that this branch sees that is described by a differential equation is this capacitor here, right? The resistor is, you don't need a differential equation to describe that. But the first element that is described by a differential equation that this outlet sees is this capacitor. This means that here at this boundary here, you have a Newman boundary condition, in which case the 0D model is expecting flow information to be provided by the 3D model, and the 3D model is expecting pressure information to be provided by the 0D model. Now you can imagine that if we're trying to run this whole simulation without the 3D model, then you need something that you no longer have the 3D model that can provide flow information at this point. So you need to basically manually add in flow information at this point, and that's what we're going to do. Now, if the so this is, in this case, the capacitor is the first element. Now, in the case if an inductor is the first element, then the situation will be reversed, where you would have a Dirichlet boundary condition, which the 0D model is providing flow information to the 3D model, and the 3D model is providing pressure information to the 0D model. And so if that's the case, then you would need to manually provide pressure information to your 0D model in order to be able to run it standalone by itself. And so basically the pressure and flow is reversed. The situation is reversed for a Dirichlet boundary condition. But I'll show you how to do that with a Newman boundary condition, and you can apply the same principles if you have a Dirichlet boundary condition. And so to do that, it's actually very simple. So here's the files that we have from last time, the multi-scale simulation files. And what we're going to do is we're going to go into this boundary condition folder. We're going to open user.f. So in user.f here, there's a couple things we have to change. And so as I said before, in a multi-scale simulation, you have the 0D model that is expecting, in this case for a capacitor, it's expecting flow information to come in from the 3D model. But if we want to now bypass the 3D model, then it is no longer expecting the flow information that it's getting will not be from the 3D model. So we need to comment out this line. This line is telling the program, so this program here is our LPN program. This is the 0D model. And right now, before I comment it out, it's saying that it's expecting either pressure or flow information from the 3D model. But since now we don't have the 3D model, it will not be getting those information from the 3D model. So we're going to comment out this line. The next thing we're going to do is basically, since now there's nothing that will provide, well, we don't have the 3D model to provide the flow information to our capacitor, we need to manually tell the capacitor what is the flow that's coming in from here. And so you basically need to add in some equations that will tell the program what the flow is when it's trying to use it. So in this case, remember in our differential equation, we're using this Q, which is the flow that's coming out of these branches. And so before we're getting this Q from the 3D domain, but now we're bypassing the 3D domain, but it's still trying to use these Q terms. So we have to tell the program what these Q terms actually are. And so the way that we do that is we basically add in equations. In this case, I'm just going to combine everything into the same equation. Um, and since I'm using Q3 and Q4, I have to tell it what Q3 and Q4 is. And so in this case, I'm just going to say that this is a decision I'm making. I'm going to basically just say that this 3D part does not exist. So whatever pressure that is coming in here, that would be the pressure that's driving these flows. And so I define Q3 and Q4 as this pressure minus these pressures in the capacitor and divided by this resistance. And so um, I'm manually prescribing the flow to be the flow of this pressure drop across this resistance, and the same thing here. And you can define this differently if you want to. You can pretend that this section is some value of resistance or anything else that you want, and you would basically just define these Q's differently at these points depending on how you want to approximate your 3D model. But for now, I'm just going to approximate it as something that basically doesn't exist. And so I provide the Q information here. And so that's all I have to do in the user.f file. Now remember that we commented out this line for the 0D only testing. Now if you're done testing and you want to go back to run your multi-scale simulation, just remember to uncomment this and then comment this out, because now we need the Q that's actually provided by the 3D domain but not calculated in this user.f. And so just remember, when you're done testing or debugging, you want to change everything back to what it was before so that it'll run with the multi-scale simulation. Okay, so now we're done modifying user.f. There's one more thing we have to do. So we have to go into this test.f file. And this file basically kind of simulates the 3D part of the multi-scale simulation. And so there's just a couple of things that you have to pay attention to or to change in this file. You have to tell it we have to decide how many steps we're going to run in this 0D only simulation. And so here's the number of steps per cardiac cycle, and here's how many cardiac cycles you want to run. And so if I put 1,000 here and put a 5 here, that means I want to run a total of 5,000 steps in my standalone simulation. This is number of phases, and so you should set that to be consistent with however many phases you have here in phases.f. And so in this case, we have 4 phases, and so I'm gonna set this number to 4. And then this nx would be the number of x variables that you have. So however many x variables you have in your user.f. So in this case, we have 6 variables up to x6. So I'm gonna put 6 for this number right here, and you don't have to worry about this one. And then here you have to put the name of the initial values, where you have the initial values, and that's it. You don't have to change anything else in this file. And so I'm gonna save this, and now you're ready to run a 0D only simulation of your multi-scale setup. And so I'm going to go to this folder with my terminal, and I'm going to compile the boundary condition, and it's generated a file that's called test.exe, and this is the file that you would use to run your 0D only simulation. And so I'm going to execute this test, and basically now it's running the simulation, and when it's done, it'll create this all data file, which is basically the same as the all data file that you would get from your multi-scale simulation. So now you can go in here, load this in MATLAB, and check to see if the values make sense. And so this is how you would run a standalone 0D simulation of a multi-scale simulation. Once you've done this, you've debugged and checked to make sure that your circuit, the LPN circuit, is correct. You could change these things back. Basically, you would uncomment this and get rid of your Q calculation, save this file, and then you will be ready to run your multi-scale simulation again.